Hi, everyone. Thank you so much for coming. My name is Mark Sagaitis, and I lead the Location and Context Client team. And with me are Wei Wang, Steve Malkos, and Shobik Sen. And we're really excited to be speaking with you today about what's new with Android sensors and location. Now, we'll start by discussing some of the upcoming changes to background location and how you can prepare your application for the Android O release. We'll then discuss accuracy improvements to location, improvements to activity recognition, as well as sensors. So let's get to it. Well, I think we've all experienced that terrible feeling when your battery is just about to run out. It's a beautiful day outside, so you decide to go for a hike. And after several hours, you come up to a beautiful baby deer. It's super cute, and you manage to get really, really close to it, closer than you've ever been. And you decide you're going to take a picture. Now, this is going to be the best picture you've ever taken. So you slowly, carefully take your phone out of your pocket, push the power button, and your phone is out of batteries. So not only do you miss the shot, but then you realize you're not exactly sure where you are, and you're really counting on your phone to help you navigate back. And all of a sudden, the woods look like a much scarier place. So I think the point here is that battery life is extremely important to users. In fact, 1 in 3 users say that battery life is the #1 problem on their device, the #1 problem. This is also apparent in statistics we track about location. So a large percentage of users have decided to completely disable location on their device. And when we asked them why, they said power was the main reason. Now, this is a problem for every developer in this room who uses location, since when location is disabled, just a lot of stuff breaks. From navigation to context-aware apps, I mean, even the weather just doesn't work whenever location is disabled. But I think more importantly, users turning off location means that they're not happy with the experience they're getting. And we don't want that. I mean, we want users to absolutely love location. So we've taken a really close look at power consumption, and here's what we found. Well, for one thing, location is used a lot. The location APIs currently allow applications to request location at virtually any time. So every bar you see here is a device doing some kind of location-related work. Now, we can analyze the cost of these using something called Android Power Primitives. This is something I'm really excited to be speaking with you today about. This is the first time we've talked about these externally. So you can think of Power Primitives as a way to understand the fundamental building blocks of power on an Android device. And we can use these to really understand sort of how location power is computed. Here are the 4 basic operations that consume power when using location. We first have to wake up the device to perform some work. We then have to get some location signals, like Wi-Fi and GPS. Then we have to run some computation on the CPU, and then finally maybe go to the network to get some more model information. And we can understand the cost of all of these by using the power primitives. So this is the cost of every single one of these operations. There's a lot going on here, so let me highlight the most important ones. Well, first, using the cell network is extremely expensive. This is why the location stack has been heavily optimized to cache data locally whenever possible and try to avoid going to the network by computing things locally. Also, obtaining location signals is expensive. For example, the first fix for GPS can cost quite a bit. This is why we usually tend to prefer doing Wi-Fi scans instead. But unfortunately, Wi-Fi scans are not really cheap either. So what we've been doing is try to reduce the cost of these as much as possible by limiting which channels we look at when doing a Wi-Fi scan, as well as spending the least amount of time possible on each channel. But we are coming up to some physical limits to how much we can optimize here. So in summary, we see that power is extremely important to users. Unfortunately, location is not cheap, and we're coming up to some pretty hard physical constraints as to where we can optimize. And as well, there are some amazing features being built using location. So with all of this in mind, we're introducing a significant change to how location works in the Android O release called background location limits. This is something we're really excited about, as it drastically improves battery life for Android users while also allowing great location use cases to be built. And now Wei will come speak to you about some of the details of background location limits, as well as how you can prepare your application for the Android O.
Okay. Thanks a lot, Mark. My name is Wei Wang. I'm a software engineer in location and context team. I'm going to talk about background location limits in Android O release, the power improvements to location APIs, as well as how you can prepare your application for these changes. So first, let's take a look at the difference between foreground apps and background apps for location purpose. An application is considered as foreground when it is actively interacting with users, which means it's either running a foreground UI or running a foreground service that the user cares about. Otherwise, the application is considered as background from location perspective. So our study showed background apps are the major contributor to location power issues. Now, before Android O release, there were no limits to background location usage, which means any app can request location at any time. Now, this causes several different problems. As a result, many applications request location aggressively when they run in background, or they leak a fast foreground location when they switch from foreground to background. So beginning from O, we're going to impose limits to the background apps. Now, so I would like to emphasize these limits apply to background location only and would not affect your foreground location usage. So let's start with location providers. Location providers are the main entry for requesting location updates. We have two main location providers: the field location provider in Google Play Services and the location manager on the platform. So starting from Android O, for both location providers, apps running in background cannot trigger location computation more frequently than a couple of times per hour. For batching API in field location provider, a few more location computations are allowed. But the delivery time is going to be the same as non-batching API. So for field location provider, we're also going to take advantage of Wi-Fi connection to reduce location computation. No new location computation will be performed when the device is connected to the same access point, which indicates the user has not moved much from the previous location. So this provides significant battery improvements when the user is at home or at work with Wi-Fi connection. So with similar strategy in mind, we also applied very similar changes to geofencing. The responsiveness of geofence will increase from tens of seconds to a few minutes. But the power is going to be 10 times more power efficient than the previous releases. So we also use similar Wi-Fi connection approach and can now provide better transition detection when the user leaves home or leaves work. So all the changes I mentioned apply to all background apps running on Android O release, regardless of the target SDK version. We believe this is the best approach to provide users with immediate battery improvement when they upgrade to O. Now you may be wondering, how do these changes look like on a real device? So Mark showed you an example of location activities before O. Now let's take a look at how things change after applying all the background location limits. So you can see there are much fewer location activities during the same period. In fact, after around 6 p.m., when the device connected to a static Wi-Fi access point, there was no location computation. But we were still able to provide fresh locations because we know that the device is connected to the same Wi-Fi, so the user has not moved far away. So the battery consumption for background location is much, much better now on O. OK, so I've talked about a few changes to background locations and the battery improvements. The battery looks really good. But as a developer, you may be wondering, this means fewer locations coming to my app. What should I do? So let's talk about a few approaches that you can take to make your application ready for background changes. So first, consider only request foreground location. So does your app really need location when it is not interacting with users? If it only needs user location to search restaurant nearby, then you can always request a location after the user opens the app. No background location limits would apply in this case, and you can get frequent location updates as before. So we are also working on reducing the current location latency to ensure a better foreground location. On the other hand, if your application needs to trigger when the user enters or exits a given area, such as automatically turning off air conditioning when the user leaves home, you can use geofencing API to detect the user has entered, dwelled, or exited an area of interest. As mentioned before, the geofencing API in Android O is 10 times more power efficient than the previous releases. If your application needs to collect the user's location and display the location history at a later stage, such as Google Maps timeline, then you can use Beijing API in Field Location Provider. Beijing allows the location system to collect location signals, such as Wi-Fi scans, at low power with a higher rate, then compute and deliver locations to the client only when needed. This way, we can consolidate all the network queries to save battery. So let's take a look at an example of how to enable location batching. As usual, you will need to create a location request. You set the interval to 10 minutes. The key here is to set the max wait time to a few times more than the request interval. So this allows location provider to collect location signals every 10 minutes, but deliver the location to the clients every 30 minutes. Now, finally, as a last result, if you really need unthrottled foreground locations when you're running in background, you can start a foreground service by showing an ongoing notification. Applications showing ongoing notifications are considered as foreground apps, so background location limits will not apply. To start a foreground service, create a notification and supply a pending intent to be called when the notification is clicked. By calling start foreground, or if your app targets Android O, call start foreground service, the service becomes foreground while you're showing ongoing notifications to the users. Now, do not forget to stop foreground service if foreground location is not needed anymore. OK, so far I've talked about background location limits on the Android O device. How about pre-O devices? The system did not impose any limits on pre-O devices, so we rely on your best practices to make sure the background location power is at a reasonable state. The optimization you do, such as request only foreground locations, use geofencing instead of frequent location polling, using batching if immediate location is not needed, can very well be applied to pre-O devices to make the background location usage, battery usage at a reasonable state. OK, so in summary, I've talked about background location limits, battery improvements for locations on O, and several different ways to make your apps ready for those changes. Now let's switch gear to talk about location accuracy improvements. Thank you. For the past years, we have been keeping on improving location accuracy, especially for indoor environment. Our data showed a 40% and 20% accuracy improvement for the past 2 years. This year, we are on a good track of achieving another 40% better accuracy improvements, and another 40% accuracy improvements in the year 2018. In fact, our accuracy would be good enough for indoor navigation. Now, let me show you a couple of videos to demonstrate our indoor accuracy improvements. So the left side video is running on the current field location provider. The right one is running on a version that comes soon. The blue dotted line shows the route the user was taken. The blue dot, as usual, is user's current location. Now let's play the first video. So you can see the blue dot aligned with the user's real location reasonably well at the start. But as the user went deep indoors, the location jumped and diverted a lot from user's real location. OK, now let's play the second video to see how things improved. So this time, the blue dot aligned with the route perfectly well, even when the user was deep indoors. Now, when the user makes the turn, you can see the algorithm track the move really well. So we are very excited about the accuracy improvements, and we hope this can bring better opportunity to your application. Another area we are truly excited about is the support of the raw GNSS measurements in Android N release on Location Manager. Developers can now get more information, such as pseudo-ranges, Dopplers, and carrier faces, other than just the position. The information can be used to build value-added apps, such as much more precise positioning using carrier face measurements. We also provide tools to log, analyze, and visualize all these GNSS measurements. You can use these tools when prototyping your apps and answer questions like, which satellites are in view? How strong are the individual measurements? How accurate are the range measurements? We are very eager to see more use cases of the raw GNSS measurements in the ecosystem. Okay, so far we talked about accuracy improvements to field location provider, the new APIs for GNSS measurements. We hope developers can take good use of these improvements to build better location apps. With that, I'll hand over to Mark to talk about activity recognition.
Cool. Thanks, Wei. So activity recognition provides your application with contextual cues as to what users are doing in the real world. And now, these are the activities we currently detect. This is something I'm extremely proud of, as just a few years ago, this list was much smaller. So you can break it down into fitness-type activities, like running or biking, device context, like are you in a vehicle, as well as some gestures, like the tilt-to-wait gesture on your watch. And today, I'd like to talk to you about some upcoming improvements to our accuracy, some simplifications we're making to our APIs to make them much easier to use, as well as some new activities we'll be detecting. So let's start with accuracy improvements. Well, the world of machine learning has seen some amazing results from the use of deep neural networks, and activity recognition is no exception. We've developed a deep activity neural net, which significantly improves the accuracy of activity recognition. Now, this makes it much easier for you to build contextual applications, and it also looks really cool. We're also doing some big improvements to our APIs to make them easier for you to use. Now, the current activity recognition API provides you with raw, low-level access to activity signals. Now, this is very powerful and flexible, but it also means that simple things can be hard to do. So let me show you what I mean. Now, let's say you're building a car assistant app that allows users to interact with their device hands-free when in a car. Now, a simple way to do this would be to write an if statement that says, if the activity is in vehicle, start my app, and if it's not in vehicle, close my app. So let's talk about some of the pitfalls that you'll encounter if you do this. OK, so the user starts in a vehicle with a confidence of 80%. Great, so far so good. You launch your application. And he keeps driving with a confidence of 100. Everything's working well so far. And then he stops at a light, and you get a still activity. Now, that simple if statement from earlier wouldn't have taken this into account, and the app would have closed. So you say, OK, let me update my filter to deal with the still while in vehicle use case. So the user continues to drive, and then hits a speed bump, and we misdetect it as biking. Now, we work really hard to avoid misclassifications, but sometimes they're unavoidable in this kind of raw, low-level API we're providing that has very little filtering in it. Now, you can write a filter to try to deal with things like this, because if you look at the history, well, there was a lot of driving in the past. The biking confidence is very low, so 55 is pretty low. And there was no activity that you would expect between driving and biking, like something like walking. But writing this is getting pretty cumbersome and complicated. OK, so the user continues to drive. And now you get a tilt event. Now, a tilt event is a strong indication that the user's activity is about to change. It tends to happen when a user goes from sitting to standing. So you can take that into account into a filter. And then finally, the user starts walking, and you can finally close your application. Now, writing a filter to deal with all of this is pretty tricky and requires a lot of training data to get right. Well, we're making this much easier with the Activity Transition API. Now, it takes a messy, raw activity signal like this and turns it into simple transitions. You get a vehicle start event when the user starts driving, and a vehicle end event when they stop. That's it. We take care of all the filtering behind the scenes. This means that by using this Activity Recognition Transition API, you can write that simple if in vehicle statement, and your app should just work. Oh, thank you. Now I'd like to quickly talk about some of the new activities we're working on detecting. So we're really excited to announce that we've developed a road versus rail vehicle detection algorithm that can tell the difference between a car and a train, for example. So we think this will lead to some very powerful applications that help users during public transit, as well as improve in-car experiences. And we can't wait for you to try it out. And I'm also really proud to announce that we're now able to automatically detect strength training exercises. This means that you can walk into a gym and have your entire workout automatically tracked for you. This makes it really easy to keep track of your progress over time and make adjustments along the way. It's available on the LG Watch Sport, and we'll be rolling it out to more devices soon. So in summary, activity recognition will be bringing you improved accuracy, simplified APIs, and new activities in the coming month. And now, I'd like to invite Steve to talk about how we'll be making this, as well as other contextual use cases, run at ultra-low power.
Awesome. Thanks, Mark. Hi, my name's Steve Malkos. I'm the technical program manager for the Android Location and Context team. Before I start talking about Android Sensor Hub and Context Hub runtime environments, can I see a show of hands? How many people here know what the Android Sensor Hub is? Not that many of you. That's all right, because when you leave here today, you'll all be experts in this field. All right, Mark just showed us some really cool examples on how activity recognition works. We've launched some amazing features in Android, things like physically tracking where you're parked your car, tracking your activities like running, walking, and biking, and providing you with relevant information that's important to you at a specific moment in time, like pulling up a train schedule as you arrive at the train station. But we found that bringing some of these factors, some of the biggest limiting challenges here, has been around power, consuming power. That's your battery. So with the Android Sensor Hub and Context Hub runtime environment, we're able to leverage the capabilities of a low-power processor to make it possible for us to bring these experiences and more. We all know that if you write an application and it sucks up the user's battery, they're going to quickly uninstall it from their device. When talking about power for activities that happen in an always-on fashion, there's always two things at play: latency and accuracy. Improving power means we could run our apps at a greater frequency, improving on the latencies. Improving power also means we could look at more signals, improving on our accuracies. So 2 years ago, we introduced the Android Sensor Hub in Marshmallow. We used this tiny standalone microcontroller that's depicted on a dime and connected all the sensors to it, and it runs in an always-on fashion. We launched this on the Nexus 5X and the Nexus 6P. Last year, we worked on the second generation of the Android Sensor Hub. This time, in addition to connecting all the sensors to it, we also connected all the wireless connectivity components. And we launched this on the Pixel and the Pixel XL. As mentioned earlier, the Android Sensor Hub runs in an always-on processing, and it hardly affects the user's battery. Context Hub runtime environment provides a common platform for us to leverage these low-power processors. So with the Context Hub's common platform, we created mini applications that we call nano apps. And so let's go through a couple nano app examples. All the activity recognition APIs, like running, walking, biking, and vehicle, have been ported from the main application processor into the Android Sensor Hub. We'll take a look at how activity recognition both saves on power and improves on our accuracies when running as a nano app. If you were to run activity recognition on the main application processor, it consumes a ton of power, about 5 milliamps. When we introduced sensor batching in the Android operating system, we were able to cut that number down into half. But it's still running on the main application processor. We took it from 5 milliamps to 2.5 milliamps. Running these same algorithms in the Android Sensor Hub as a nano app costs us a fraction of that power, 300 microamps. And because the power is so low, we can now run these algorithms at a faster frequency, improving on our latencies and our accuracies. Another example of a nano app that I'd like to highlight is geofencing. There are tons of geofencing applications in the market today that use the Google geofencing APIs. We've now offloaded these algorithms from the main application processor into the Android Sensor Hub. And we did this by connecting the Wi-Fi chip, GPS, and the cell modem into the low-power compute domains. This brings us a significant power savings, and it improves on our latencies. And finally, on the Android Sensor Hub, let's talk about gestures. We added tons of gestures. Gestures like lift to check phone, double tap to check phone, flip camera, and more. I'm going to highlight one of the examples, and let's focus on flip camera. If I launch my camera app and double twist it, it will change from outward facing to selfie mode. I have to do this. All right, everybody on the count of 3, say cheese. 1, 2, 3, cheese. All right. This gesture is only possible because it runs in an always-on fashion in the Android Sensor Hub. Any application could register and use this private sensor type today. OK, to close on the Android Sensor Hub with CHRE, devices on the market that support this automatically get a common platform that takes advantage of lower power, lower latencies in an always-on compute fashion. And these nano apps can overcome some of the new paradigms that have been introduced with our latest operating system, like background location limitations. We're really excited about this platform and the new use cases that could be enabled from it. I'm going to switch gears now and go from that to Android sensors, highlighting 4 key items. And then Sulvik's going to come up and talk to us about the Compass. Dynamic sensors. This was introduced in Android N. It allows us to expose sensors that are not necessarily bundled with the device. And it lets us connect them via Bluetooth and USB. For example, you can now attach a high-quality inertial measurement unit to your device, biological sensor, environmental sensor, and your apps could natively see them. This year, we're standardizing on these interfaces for dynamic sensors. So the sensors that you build can now leverage the Android platform and make it easier for you as an application developer to access them. Direct Sensors Channel, initially targeted for VR and camera applications. Simply put, Direct Sensors Channel is minimal latency between the sensor driver and your application by bypassing the sensor service. Accessing sensors directly with Direct Sensors Channel, the programs that you develop will have the smallest amount of sensor latencies. Ever experienced a VR application with a skewed horizon? Similar to uncalibrated magnetometer and uncalibrated gyroscope, we introduced uncalibrated accelerometer. Last year, we wrote our own calibration algorithms for the accelerometer, and we open sourced this to the ecosystem with the hopes and goals that a device manufacturer would build better devices. And we're seeing results like this. After applying the calibration algorithms, the VR landscape is straight. Final sensor feature that I'm going to focus on is wrist sensor, now called low latency off-body detector. Simply, we have a reliable way to detect when the watch is on the wrist or off the wrist. The targeted use cases for this is low friction authentication to your phone, no passcodes for payments, and changing the UI behavior when the watch is off your wrist, like sleeping the watch more aggressively when it's off your wrist. So before I hand the microphone over, I want to quickly note that we use sensors today in almost every application, and our commitments to them at Google is huge. We'll continue to invest in this sensor's future. These features like dynamic sensors, direct sensors channel, calibration algorithms, and low latency off-body detectors are just a few highlighted examples on what we're working on. We'll be adding more sensor features in the future. With that, let's continue on the sensors theme and hear from Sulvik on the Compass.
Thanks, Steve. I'm Shovik Sen. I'm a software engineer in the Android location and context team. And I'm here to talk about heading and bearing. So what is heading and bearing? So bearing tells you, as a context, the direction that the user is traveling. And heading is the direction that the user's phone is pointing. So heading and bearing are different. Like heading is something that if you are standing at a stoplight and you pan your phone around to find which direction you should walk, that's when your heading changes and your bearing is not necessarily changing at that point. So how do you utilize bearing and heading depends a lot on the user's context. So if you're an application who might gain by knowing the direction of the user, think very hard about what context you're after, because based on that, you want to select between heading or bearing. Let's see how we are doing that in Android Google Maps. So in Android Google Maps, the blue dot arrow used to always point to the user's heading, essentially which direction your phone is pointing. Now, what we found is that the user's expectation from the blue dot arrow is much more. When they are stationary, like standing still or panning their phone around, they want to see their heading from the blue dot arrow, perhaps because they are trying to figure out which direction to go next. If they're traveling, like in a car or in a bicycle, or even when they're running, they want to see the bearing. That is the direction that they are moving, because they want to perhaps verify that the direction they are going towards is actually correct. And more importantly, they want us to communicate the uncertainty in heading or bearing. Because if we are not certain if the heading or bearing information that we are giving to the user is not correct, the user wants to look around and orient themselves and be diligent about this. So how do we do this? To distinguish between stationary and traveling, we can use the activity recognition API that Mark just talked about. You can know when the user is stationary versus traveling and choose between heading and bearing based on that. Now, to determine the uncertainty, note that bearing is based on location. So you can see what the location speed is and what the location accuracy is, and based on that, you can determine if the bearing is correct or not. But how do you find heading uncertainty? To understand that, let's see how heading is actually being computed. So heading today is estimated based on the phone's compass. And as many of you know, the phone's compass can be very unreliable in presence of metal objects or external electromagnetic fields. Simple cases where, like for example, if you're in a car, or you're charging your phone, or even simple things like you keep your phone next to your laptop, it's possible that the phone's compass will become uncalibrated and hence becomes unreliable. And all of this ties to the heading uncertainty that we are after. So in a nutshell, what we found by looking at a lot of data is that heading uncertainty really is about what is the environmental uncertainty in which your device is at. Now, to understand the environmental uncertainty, we found machine learning can actually help us. There is only a few kinds of environmental uncertainty or anomaly that we are after. And if you have enough data, machine learning can tell when there is anomaly, and hence when the compass is correct and when the compass is not. And that ties into heading uncertainty. We can tell the user, oh, your heading is probably not correct because the compass is unreliable. And moreover, now, because we know that when the compass is unreliable, we can go back to other kind of sensors like gyroscope, and this in return actually improves the heading accuracy significantly. So now that we know the heading uncertainty, let's see how we can communicate that using in Android Google Maps. So before, in Google Maps, we had this pointy cone, which will always point to heading. But now, because we know the heading uncertainty, we have a cone EY, where the width of the cone now tells you what is the uncertainty in heading. If it's too wide, you know that the heading is probably not correct, and hence you can look around and try to orient yourself. If the cone is narrow, you know it is correct, and you can just use it for your own travels. Beyond Android Google Maps, if you are an application who might benefit by knowing the user's direction and also the uncertainty in a more correct fashion, we are happy to announce that this is something we are going to bring in for all applications with the Fuse Location Provider API. With this, I will hand over to Steve to talk about the future of Android location and context. Thank you.
Awesome. Thanks, Solvik. I love talking about the future. So let's talk about the present with regards to testing location quality, because that's the key to making future improvements. Over the past few years, we've gotten very serious with regards to testing at Google. We've built up massive labs and real-time tests from around the world measuring our location quality. For example, we run running tests, walking tests, biking tests, stationary tests, testing both indoors and outdoors. When driving near tall buildings, it's very common for your GPS position to jump, lag, or even drift. At Google, we use very expensive military-grade inertial measurement unit that gives us centimeter-level accuracies that gives us this ground truth. That's the image at the top, the San Francisco test setup. The image at the bottom shows our running and pedestrian test setups. The output from these tests is the graph, where we show a cumulative distribution function on the position errors from each device as measured from the ground truth. OK, project elevation. Before talking about this, I want to quickly note about a service that we launched last year called Emergency Location Services in Android. This service gives us the ability to use the computed location in Android and send it to emergency responders during an emergency situation. So for example, if you dial 911 or 112 on your handset, the computed position from Android will go to carrier's network and public safety answering points for those carriers who sign up for this free service. All right, with that in mind, Project Elevation. Many places around the world, like downtown San Francisco, when you're deep indoors, your 2D Latin lawn are just not enough. GPS altitude works great when you're outdoors, but barely works, if at all, deep indoors. And we especially need it when we're in environments like this. So with Google's machine learning algorithms, anonymized crowdsourced models will soon be launching Project Elevation this year. This service will first be utilized by our emergency location services in Android, where we hope to see first responders benefiting off of it. And then we'll also launch it as part of the standard Android location altitude outputs, so you as a developer could get access to this as well. We'll also bring a new class of 3D accurate indoor location. You heard part of this from Wei. By using Wi-Fi, GPS, cellular, PDR, IMU, altimeter, we're just around the corner from launching this massive improvement. And we'll get there again by using Google's machine learning algorithms, anonymized crowdsourced models, to give us these better accuracies where we can now navigate indoors. Then, once we have this all running on the main application processor, we'll port it down into the Android Sensor Hub, because that's the key. 5 meters at 0 seconds time to first fix at ultra low power. OK, the GPS geek inside of me gets really excited when we talk about dual frequency GNSS receivers. L1 plus L5 signals. What does this mean to you? Better GPS performances. We'll bring this into smartphones in the next couple of years, and we'll do so for the following reasons. Better ranges for multipath mitigation, because we'll be using a higher chipping rate, 10x higher. It will give us unprecedented frequency diversity using the L1 and L5 signals together. Our Android O APIs already have full support for multi-frequency GNSS receivers. This enables many use cases. I'm just going to highlight 2. Better downtown urban canyon performances. No more positions on the wrong side of the street. Post-processed decimeter level accuracies. Any application that needs really precise location will benefit off of this, like fitness applications, traffic info, and more. So at work, we get to work on some really cool, amazing new stuff. Let's put this all together. The future will become more and more contextually aware. We'll continue to add more signals into the Android Sensor Hub. We've already achieved activity recognition and geofencing. Next, we're going to add the Fuse location provider, awareness, places, and more. We'll do this with deep neural networks, machine learning algorithms, and our personalized models with the goals of helping you make deeper experiences to your users in your applications. By adding all these signals, we'll reach a point of location and context singularity, where you'll be able to write applications that simplify user interactions, help augment human memory and knowledge, and your users having a better understanding of themselves. I'm truly excited about this future and all these possibilities. Thank you very much.